All right, good afternoon, evening, or morning, ladies and gentlemen. Welcome back to another episode of CS341 Algorithms, where we typically meet in person semi-weekly, but we're going to be meeting online instead from here on out. And here on out means for this lecture and for 3 more after this. And I'm going to be your instructor for these 4 lectures. And hopefully we can all have a reasonable conclusion to the course. We're certainly going to be trying our hardest as instructors to make this as painless as possible for you guys. And for my part, I'm dumping as much effort as possible into preparing the slides to try to give you guys the smoothest content delivery possible. So this time, we're going to sort of briefly wrap up at least what my sections were almost finished but hadn't quite finished last time we met, which is we're going to try to finish up the FLOYD-WARSHALL algorithm, which is a solution to the all pairs shortest path problem. And if this is something that you already feel pretty comfortable with and you've covered in your section, then of course this is a video, so you can skip ahead. And then I'm going to talk a little bit about formulating graph problems, about problems that don't necessarily look like they should be graph problems, but actually can be expressed very elegantly as graph problems. So you can kind of harness the wide variety of powerful graph algorithms that are well studied and exist to solve your problems. And then we're going to talk a little bit about intractability. We're going to start this final section of our course where we discuss the relative difficulty of problems. And so we're going to talk today about decision problems, a class of such problems called Polynomial-time algorithms. We're going to talk about polynomial-time Turing reductions, which are sort of similar to the reductions that we've seen so far in the course, but with some extra sort of constraints on polynomial runtime. And then we're going to talk about some reductions to sort of demonstrate how polytime Turing reductions work. Okay, so let's start with the FLOYD-WARSHALL solution to the all pairs shortest paths problem. Here's a little bit of a refresher for you. So what is the all pairs shortest paths problem? Well, we're given a directed graph, G, and a weight matrix M. And the weight matrix M, okay, what is this weight? W of ij so this is defined for every pair of nodes I and j. You have this wij. If ij is actually an edge in E, then this capital W of ij is just, it's the weight of that edge from I to j. Now if I equals j, so conceptually wij then is wii. It's the weight of the edge from a node to itself. We just say that, every node has a self edge of weight 0. You can get from yourself to yourself with 0 cost. And then if there is no edge from I to j, and I to j are distinct, then the cost is just going to be infinity. And infinity, in reality, can actually just be, if you implement this on a real system, there's no infinity number, at least not for integers, right? So if you want to represent this infinity, you sort of can reserve one integer, like max int, to be your infinity, and any smaller number is considered to be finite. And the purpose of this infinity is just to make sure that, a shortest path can't possibly contain an edge that doesn't exist, because the whole weight of that path would immediately become infinity. A minor note about implementation details. If you choose your infinity to actually be like max int, the max value representable by your data type, you have to be a little bit careful about adding infinities, because adding infinities might cause your number to wrap around and become negative, or just cause you to wrap around to a smaller number if it's an unsigned integer. So be a little bit careful about your choice of infinities, and be very careful about adding infinities in practice if you have to implement this. But at least conceptually, this is how W is defined, and sort of that's an idea what the purpose of that infinity is. And the goal of the all pair shortest paths problem is to output basically a matrix of results. So it's going to be a two-dimensional matrix of results. We're going to output D of ij, where D is the distance from I to j, the optimal distance on the shortest possible path from I to j. We're going to do that for all I, for all j, for all pairs of I and j. So you're going to be outputting, if there are n nodes, you're going to be outputting n squared optimal distances. And if there is no path from I to j, then of course the optimal distance should just be infinity. Okay, so that's the problem. And we're actually going to allow negative weights in FLOYD-WARSHALL, unlike Dijkstra's. We're going to allow negative weights. So this is like Bellman-Ford allows negative weights. We're going to allow negative weights in FLOYD-WARSHALL, but we're going to assume that there are no negative weight directed cycles in G, because if there are any negative weight cycles, then this problem is not really well defined, because there isn't really a shortest path. Because if I can sort of travel from a node I to some node on a negative weight cycle, and then I can travel around the negative weight cycle, and I can just continue adding trips around this cycle, reducing the total cost of my trip to, I can continue doing this basically forever, and I can always come up with a shorter path from I to j. As long as I can get from I to a negative weight cycle and from that negative weight cycle to j, I can always come up with a shorter path from I to j by taking one more trip around the negative weight cycle. So basically, the paths from I to j essentially become negative infinity. So we just rule out negative weight cycles. Whenever we're talking about shortest paths, we never allow negative weight cycles. Okay, so to remind you a little bit about the solution to FLOYD-WARSHALL, it was a dynamic programming solution. At least in my sections, it was the third of three dynamic programming solutions that we saw. And of course, in a dynamic programming solution, you have to relate the problem that you're solving to solutions to subproblems. So you want to relate the optimal solution that you're looking for to optimal solutions to subproblems. And the way that we defined our subproblems in this case is we're going to shrink our problems to subproblems by restricting the nodes that are able to be used in our shortest paths. So our subproblems are going to be the shortest paths in which all interior nodes are in a specific set. Specifically the nodes 1 up to m-1. So you're allowed to use the first m-1 nodes as interior nodes on your paths, and the question is, what's the shortest path I can get from I to j if I'm only allowed to use a subset of these nodes, of these first m-1 nodes as interior nodes on those paths? And to ensure optimality, we of course argued optimal substructure last time we talked about this, and we of course can't tell, which particular node is being used, which particular nodes are being used on the path from I to j, but we can sort of consider, whenever we introduce a new node, whenever we talk about increasing the size of our subproblems, by 1, so we're trying to solve a bigger problem in, where we're allowed to use the first m nodes in terms of subproblems where we're allowed to use the first m-1 nodes, we can use this node m. And this node m could kind of appear, anywhere on the path from I to j, or maybe not at all. And so we'll try all the different ways to use node m as an interior node, and that sort of led us to this dynamic programming formulation. So here's the formulation. Let dm I comma j denote the minimum weight I to j path in which all interior nodes are in the set 1 up to m. So m is how many nodes were, how many nodes in the set, 1 up to m. Sorry, I'm saying that incorrectly. You're allowed to use any number of vertices in the set 1 to m as interior nodes. So you can use 0 of these, you can use 1 of these, you can use all of them as interior nodes on the shortest path from I to j. That's how we define dm. This, of course, defines all of our subproblems because it's defined for all m and all ij. And we want to compute dn, which is going to be the minimum weight path from I to j in which all interior vertices are in the set 1 to n. Okay, well, what does it mean for all the interior vertices to be in the set 1 to n? That just means you're allowed to use any subset of the vertices, or maybe all of the vertices in the entire graph. So basically, this restriction in which all interior vertices are in the set 1 to n just disappears in dn. So it just becomes the minimum weight I to j path, which is the solution we're looking for. So the initialization is, d0 is just the weight matrix, because d0 is I'm not allowed to use any interior vertices. So there can't be any interior vertices on a path. A path just has to be a single edge. Well, that's exactly the weight matrix. And then we update dm as follows. So dm of ij is the minimum of, maybe we don't use the mth node at all, and it's just the best we can do with the first m-1 nodes that are sort of candidates to be used as interior nodes on paths. Or it's the best we can do getting from I to m using interior nodes 1 up to m-1, plus the best we can do to get from m to j using interior nodes 1 up to m-1 as possible interior nodes on these paths. Okay, and we argued last time, I won't do it again, we argued last time that we had this optimal substructure property where the optimal path from I to j that uses m has to consist of optimal paths from I to m using the first, at most the nodes 1 to m-1, plus the optimal path from m to j using only a subset of the nodes from 1 up to m minus 1 as interior nodes. Okay, so that's the sort of recap. Sorry if that's sort of long-winded, but you know, it's nice that this is a video and you guys can kind of skip this if you're not interested in the full detail. Okay, so here's FLOYD-WARSHALL written down in code. This is not something that I managed to cover in my own section last time. So of course we're going to let dk, ij, I have swapped k for m just because some students were sort of confused because m is usually the number of nodes. So I swapped over to k here, and I didn't swap over the picture on the previous slide because I didn't want to have to, change all the LaTeX and take a new screenshot, etc. But here, let's just use k instead of m just to avoid confusion. M is not, this shouldn't be the total number of nodes in the graph, or sorry, vertices in the graph. Sorry, edges in the graph. This should just be, the number of interior nodes. This k should define the set of nodes that we're allowed to use as interior nodes in our graph. Okay, so dkij is what we just defined in the previous slide. We know our base case, we know our recurrence, we have to turn this into code. So let's just define the way that we'll take our input. Let's take our input as an array of vertices. Actually, to be honest, this first parameter isn't really needed at all. You could just delete this first argument. I think for a future edition of the course, I'll just do that. And the second parameter w is the weight matrix, which really is enough to do FLOYD-WARSHALL. So we're going to create two new arrays, d0 and d1. These are matrices, two, n by n matrices. And the first one, we're just going to copy all of the contents of the weight matrix into d0. And then we're going to create a brand new n by n matrix that's kind of empty for d1. And we're going to actually, instead of defining every dk, having an actual n by n matrix for every possible value of k, we're just going to make use of this space-saving technique that we've seen a couple times in my sections, where if you have dk that's an n by n matrix and it only refers in the recurrence to dk minus 1, I don't need to keep dk minus 2 around when I'm computing dk. I can throw out dk minus 2, or I can reuse dk minus 2 as the new array dk. So that's exactly what we're going to do here. We're going to have dcur and dlast, and these are like pointers to these two arrays. So initially, dlast is going to be a pointer to d0. Dcur is the array we're currently computing. It's going to be d1 conceptually, so it's a pointer to d1. And every time we start computing a new k, we're going to swap the pointers dlast and dcur. So we're actually just going to reuse two n by n matrices to compute all of the different values of k. Okay, so we have three loops for k equals 1 to n, for I equals 1 to n, for j equals 1 to n. We're going to compute dcur of I comma j, and this is really a direct translation of this recurrence. There isn't much to it. Dlast, of course, represents k minus 1. Dcur represents k. Okay, so we compute all of the cells of dcur, and then we swap dlast and dcur. Cur becomes the new last. And what was the previous last, the sort of k minus 2, if you will, becomes the new dcur that we're just going to overwrite. We're going to treat it as if it were empty. And at the end, we return dcur. So, question for you. And I'm going to ask a bunch of questions throughout my lectures, and basically what I'm going to do is I'm going to ask them, and I recommend that you sort of think about the answers, and I'll sort of say, look, you might want to pause now and think about it and come back and hear the answer if you think you've got it, or if you're stuck and want to hear hints. And in some cases, I'll sort of leak hints as I go, and in some cases, I'll just give the answer outright. Okay, so what's the time complexity of this algorithm, and what's the space complexity of this algorithm? So if you want to try to answer this question yourself, just pause now. Okay, so the time complexity is n cubed because we have these three loops, right? And we're doing constant work in the innermost loop. And this first step, if we're allocating two matrices, it takes n by n squared time to allocate and zero out those. And then assigning these pointers, swapping pointers, that's all constant time. So it's n cubed time, and it's n squared space because we have two arrays of size n squared. Okay, now this code just returns dcur, which is this final dn matrix, which is a matrix that contains the optimal distances for all pairs I and j. That's the optimal distances, is the lengths of the shortest paths between I and j. But it's not actually, you would have to reconstruct from that array of distances the actual paths if you wanted to produce actual paths. And so there is an algorithm for reconstructing the paths from this. For example, I've linked here a link to the Wikipedia entry for this reconstruction algorithm, but I'm not going to cover it in this lecture. Okay, so here's an example. I'll sort of leave this for you to go over on your own time if you're curious, but this just sort of gives you some idea how in each of these iterations where we have, D0 to start, then D1, then D2, then D3, and so on. Each time we increase D0 to D1, D1 to D2, we're allowing a new node to be used as an internal node on paths. So for example, when I go from D0 to D1, in D0, no nodes are allowed to be used as internal nodes on paths. So the shortest path from I to j is just a single edge. There can't be any internal nodes in the path. But in D1, now I'm allowing one very specific node to be used as internal nodes in the path. It's the first node. It's A. A is now allowed to be used as an internal node on the shortest path. And this actually changes some results. In particular, it changes, so sort of if we look at this matrix, if the rows are the source and the columns are the target, then this path here that's squared, I box this in. This is from C to B. So if I look at the path from C to B, the previous path, well, there was no path from C to B. It was just infinity because there's no direct edge from C to B. But now that I allow A specifically to be used as an interior node on a path, there's a new shortest path from C to B. It's the shortest path from C to A, followed by the shortest path from A to B. So it's, what is this? This is 4 plus 3 is 7 distance. Okay, so now in D1, we're allowed to use A specifically as an interior node on a path. D2, we're allowed to use A or B, or A and B, or neither, as interior nodes on paths. And so the addition of B as another possible node you can use as an interior node on paths lets you improve 3 more optimal distances. And you can kind of run through this on your own time if you like. Okay, so that was the wrap up on FLOYD-WARSHALL. Next, I'm going to talk about formulating graph problems. You might wonder what I mean by formulating graph problems. We've been solving graph problems, right? But not every problem in the real world is kind of expressed right off the bat as a graph problem, right? We give you these sanitized graph problem descriptions on assignments often where we just say, look, you have a graph, you have nodes, you have edges, solve this obvious graph problem. And I don't mean the solution is obvious. I mean it's obvious that it is a graph problem. But sometimes in the real world, you have these problems that can be solved effectively if you can first express them as a graph problem. So what do I mean? I mean, you start with some real-world problem, you define some nodes, you define some edges, and then you solve the problem. Okay. So graphs are a super important formalism in computer science. There are tons of efficient algorithms for solving all sorts of important problems on graphs, like exploring graphs, DFS, BFS, shortest paths like BFS in an unweighted graph, or Dijkstra's or FLOYD-WARSHALL in weighted graphs. Minimum spanning trees. There are all these interesting problems that have been studied, and they're actually sort of very natural fits for transforming other, not so obvious that these are graph problems into graph problems, and then we can harness this huge library of efficient graph algorithms to solve them. So, there are some problems that have very natural graph formulations, but for others, we have to do a little bit of work to figure out that it can be represented as a graph problem. So I'm going to give you a couple of examples here. These are shamelessly taken from Eugene Zima's slides. He actually has 2 more examples in his slides. If you're curious to see more examples of transforming problems that are not obviously graph problems into graph problems, I'll show 2 of his examples here, actually in a bit more detail than he showed in his slides. Okay, so here's his root beer problem. This is a very Canadian, or I guess also in the US, we have root beer, right? Nice little play on words. So the root beer problem, we have this canyon with perpendicular walls on either sides of a forest. So imagine that these horizontal walls here are like a sheer rock face that you can't climb up or get through in any way. On either side, perfectly straight lines, just because, we have to simplify our problem slightly. And then there are a bunch of trees that you can't pass through, they block you, and the trees are represented by points. So don't think of the trees as circles with any diameter, they're actually just, we're modeling them as infinitesimally small points, okay? So infinitely small points in the 2D plane. And there's this bear that wants to travel through the canyon, and we're to assume that the bear actually has a diameter. So it's given a circle of diameter d. D is an input. The locations of the trees in xy coordinates are inputs, and you can assume that the bottom wall happens at y equals 0, and the top wall happens at y equals some constant that's specified in the input. And the goal is to find an algorithm that figures out, can the bear get through the forest? Because maybe the trees are so dense or so poorly arranged that the bear can't get through the forest, or maybe there is actually a path through the forest. Okay, so let's model this as a graph problem. And the first sort of step in figuring out what you should do to model a problem as a graph problem is ask yourself, what's a sort of reasonable way to express objects in the problem as nodes and as edges, and then you can start to ask, how can I harness existing graph problems to solve my real problem on this graph? And this is an iterative process. You usually don't get this right the first time. You might have to try a few different representations where you say, I'm going to let this be nodes, or I'm going to let this be nodes, and my edges are going to be defined in this weird way or in this completely different way. So you might have to try a few different expressions, and then finally, with enough creativity, you come up with an interesting expression of the problem that captures all the constraints and allows you to solve it efficiently by harnessing a graph problem. In this case, we're going to let the trees be nodes, and the bear will just be this sort of entity that's not actually in the graph. We just sort of conceptually think of it existing. And we're going to let all of the input nodes be vertices, all the input trees be vertices, and we're going to conceptually think of there being these lines at y equals 0 and y equals h, and we're actually going to add a bunch of nodes at various places on these two lines. So in particular, for every input point, xy, for every input tree at xy, we're going to add the following vertices. Okay, we're going to add xy, the point itself, but then we're also going to add x comma 0 and x comma h, where h is the height of the upper wall. So by the way, we're sort of viewing this from top down, right? So we're looking at the bear from the top. These trees are sticking straight up towards the camera, if you will, right? And these walls are, so just so you understand the layout, the bear's trying to go from left to right. Okay, so these are the nodes that we're going to add. For every input tree, we're going to add the vertices x0, xh, and xy. So you can see I've added all these here. And now what are our edges going to be? Our edges are actually going to represent the idea that the bear cannot pass between a particular pair of nodes. So there are different ways you could solve this problem. I'll show you one potentially inefficient way of doing it. I don't think it's important that we go into a super efficient algorithm. The important thing here is how we transform something that's not obviously a graph problem into something that is a graph problem. So what we're going to do is, for all pairs of vertices, all n squared pairs, well actually now we have, if there were n trees in the input, we have 3n vertices, right? So it's like 3n all squared, like 9n squared pairs of these vertices. We're going to check for each of these pairs of vertices u and v, is the distance too small for the bear to get between these 2 points? And if so, we're going to add an edge to the graph, okay? So look, between these 2 points here, this is too small for the bear to pass through, so we'll add an edge here, okay? And this is true for this, and this pair, and this pair, and this pair. And notice we're treating all of the vertices that are on the walls just the same way as all the rest of these sort of original vertices that were in the input. So we're representing sort of collisions between, where a bear couldn't get between a tree and the wall by an edge from a node in the middle to a node on the wall, right? And we're representing impassability between two trees as an edge where neither of the two endpoints are part of the wall, right? So we do this for all the pairs, and finally we've added all of the vertices, we've added all of the edges to all pairs of nodes between which the bear cannot pass. Okay, so at this point, the only way the bear can pass through this canyon is if the top and the bottom are disconnected. Because if the top and the bottom are connected by a path, then that means there's actually this sort of wall where for every pair of consecutive nodes on this path, the bear can't get between those two nodes. So we can see here the bear cannot get through in this case because the top and bottom are connected. So once we've made this graph formulation, we can actually just test if the top and bottom are connected. And, well, how would you do that? I'll give you sort of, if you want to pause and think about that, then maybe take a moment to do that. Okay, so I'm going to assume now that you've thought about that if you wanted to. And the solution is just do a BFS or a DFS, any of these algorithms that tests connectivity. And all you have to do is, run a BFS from any point on the north wall, the first one, and just check if any point is not on the south wall is not reachable, is black. Is white still. I think I said I flipped the colors here in my head. That's right. If a BFS starts, nodes start white, they change gray, then they change black. If the top and bottom are connected, then if I run a BFS starting anywhere on the top, all of the nodes in the top and all of the nodes in the bottom should end up black at the end. So if that's not true, if some node in the bottom is white at the end of our BFS, then we know that the bear can get through. And if all the nodes in the bottom are black, then we know that the bear can't get through. Okay? All right, so let me show one more problem. So here's a problem called reliable network routing. So suppose we have a computer network with many links. The links are like Ethernet cables, and every link has a particular assigned reliability. Okay, so really they're not Ethernet cables, right? Like these are long hops, across cities or something like this. Each edge might represent a whole routing network with an estimate of the reliability. Okay, and the reliability is a probability between 0 and 1 that the link will operate correctly when we use it, to make this realistic, probably what we're really saying is let me plan a path where it's likely to be reliable for a whole hour. Here's the probability that we won't have any failures over a whole hour or something like that. And these are probabilities that exist in the real world, so every probability is actually strictly between 0 and 1. If a probability of an edge is 0, we should just delete that edge from the graph and not worry about it. And if the probability is actually 1, that doesn't happen in the real world. There's a strictly less than 1 reliability in every real world scenario. Okay. So given nodes u and v, we want to choose a route between u and v with the highest reliability, and reliability is going to be the product of the reliabilities in all the links. So if we want to go from A to D in the most reliable way possible, here's one way of doing it. This is not the most reliable way. We could go from A to B, B to C, C to D. The product of those three probabilities is the the reliability of the entire path. It's the probability that the entire path experiences no failures. Okay, so it's quite low. There's a higher reliability we can get by just going from A to B to D. So A to B is 0.5, B to D is 0.8. 0.5 times 0.8, we get 0.4. That's a better reliability. So we want to find the highest possible reliability path, okay? So it almost sounds like shortest path in a sense, right? But, obviously not, because, can we express this as a shortest path problem? So shortest path, it minimizes a sum of weights, right? So we minimize a sum of weights. And here we need, not a sum, but a product, right? So that's problem 1. And the second problem is obviously that we're not minimizing here, we're maximizing. So can you think of a way that somehow we could transform the weights in this graph so that we could sort of transform a product that we need into a sum. So by taking the sum, we would get the product. And if you want to think about that, take a moment to pause now. Welcome back. So if we want to actually turn this product into a sum, logarithms do this, right? If you take the logarithm of a times b, that's the logarithm a plus the logarithm of b. So if we maximize the sum of logs, we're actually maximizing the log of the product, right? And of course the important thing here is maximizing or minimizing or maximizing the log of something. We want to argue that by taking the log of these edge weights, we're not going to somehow ruin the optimality of our algorithm. So somehow maximizing the logs would not maximize the function that we took the logarithm of. Like if we maximize the log, the sum of logs, that's going to maximize the log of the product. We'd want to argue that also maximizes the product. Well, we'll argue that that's actually true. It's going to be true because all of the thing we're maximizing is strictly between 0 and 1, and log is monotonic. Okay, but so the second problem we have to solve here is we want to actually maximize this product, not minimize it, right? And shortest path is going to minimize. So, okay, well here's the argument that we can kind of work around that. So note, and this might take a little bit of thinking, but try to think through it. A path P that maximizes pi of w. So what's pi of w? Pi is the product symbol. We haven't seen it too much in the course, but it means I'm taking the product of all the weights on the path, all the w in p. So this is pi over all the w in p of w. So it's the product of all the weights w. So consider a path that maximizes pi of w. That path maximizes pi of w if and only if it maximizes the log of pi w. Okay, that's because the pi w product is going to be between 0 and 1, and log is monotonic. Okay, monotonic increasing and concave. Anyway, that's not so much the interesting part of this. The interesting part is we want to not maximize, but minimize. Okay, well, p maximizes log pi of w if and only if p minimizes log of pi 1 over w. So we can just take the reciprocal of the weights, and we can do this because the weights are not 0, right? We said they're strictly between 0 and 1. So we actually can do the equivalent of maximizing pi of w by minimizing log of pi 1 over w, which might be a little bit surprising. Okay, so how do we minimize log of pi 1 over w? Well, log of pi 1 over w is log of 1 over pi w. So why is that true? Well, we can just sort of move the product down here because, the product of 1 over 2 times 1 over 3 is 1 over 2 times 3, right? That's what we're doing here. And then the log of the quotient of two things is the log of the numerator minus the log of the denominator, so we get this expression. And log 1 is just 0. Okay, so that disappears. So we just get negative log pi of w. Now, negative log pi of w, remember, this is the log of a product. The log of a product is the sum of logs. So the log of the product of w's is the sum of log w over all w, okay? And there's a negative in front, so we get negative sum of log w. So that's the same as the sum of negative log w. Why am I moving the negative inside? Because we want something of the form sum of weights. Because shortest path is going to minimize a sum of weights. So we want to minimize a sum of weights. Okay, so the weights should be negative log w. So here's the solution. We're going to create a new graph where each weight in the original graph is replaced with the weight negative log w. So weight w is replaced with the new weight negative log w. Okay? And now the shortest path, from A to D, did I write the wrong thing here? I think I actually wrote the wrong thing here because, in fact, the highest, okay, so I said here the highest reliability path from A to D was the product of this stuff. That's actually wrong because clearly the highest oh no, is that right? Yeah, so this is like 0.337 or whatever. And there's actually a different path, A, B, D, that has a higher reliability. So you sort of have to disregard these exact numbers. The highest reliability path from A to D should be A, B, D instead. But so I can correct these numbers in the slides. You can go over these numbers yourself in the slides once I've corrected them. But the idea here is whatever the shortest path is going to be the sum of a bunch of negative logs. That's going to be minus log of a product, which is going to be log of 1 over that product, right? And so we're minimizing log of 1 over the product, which means that log of this product is maximized, and hence the product is maximized. Okay, so just sort of to work that backwards. And then note that so we have this graph where if we take the minimum sum of weights in this graph, we're going to end up computing the maximum product of edges in this graph. So we're going to get the highest reliability link by, the highest reliability path from A to D can be computed, although my path is wrong here. It can be computed by finding the minimum sum, so the minimum length path in this graph. Okay, so we could run a graph algorithm for solving single source shortest path in this new graph. So which single source shortest path algorithm should we implement? Should we use to solve this? Should we use Bellman-Ford or should we use Dijkstra's? It depends on whether we have negative weights or not. So do we have negative weights? It might look like we have negative weights because we have negative log 0.5, right? But remember, any log strictly between 0 and 1 is actually negative. So these are negative numbers, and we negate them to get positive weights. So we can actually use Dijkstra's algorithm to solve this problem. Okay, so in fact, you can use either Dijkstra's or Bellman-Ford. Okay, so that was the sort of crash course on formulating graph problems. Now I'm going to talk about intractability, which is the study of the hardness of problems. And so, there are these problems that are very, very hard that we don't know polynomial-time solutions to, and there are some problems we can prove are so hard they're actually impossible. So it's very important to know how hard a problem is, because sometimes you use known results about the hardness of problems and the relationship between problems to argue that you shouldn't keep striving for a better solution because I can prove a better solution doesn't exist, or I can prove that if a better solution exists, it's at least as hard as these other extremely hard problems that people have spent 40 years studying, so maybe I should stop trying to solve this very hard problem. So here's my toy example of a very hard problem. I'm sure you all have experience with this. Inserting a USB stick the correct way is, as we all know, impossible. Okay, so let's talk about problems that we're going to spend most of our time discussing, a class of problems that we're going to spend most of our time discussing the hardness of, and these are decision problems. And you guys have seen decision problems before in the course, so what's a decision problem? It's just a problem that returns yes or no, true or false. It just has this binary output, a single bit of output. We call it a decision problem because the whole goal of the algorithm is to decide, is the answer yes or no? And I'm going to give you this, a sequence of definitions here, try to make sense of them. They're going to be super important for the remainder of the course. So a problem instance is just a problem input. Instance and input go hand in hand. They're synonymous. They mean exactly the same thing. So a problem instance is it's an input, a specific input for a specified problem. And a problem solution is the correct answer, yes or no, for the specified problem instance. Okay, so this is an instance of a decision problem, a solution to a decision problem. So it's the correct answer, yes or no, for the specified problem instance, because every particular input has a correct answer, yes or no, if this is a decision problem we're trying to solve. And those inputs for which the correct answer is yes, we call those yes inputs or yes instances. And the inputs for which the correct answer is no, we call those no instances or no inputs. And of course, we have to define what the size of a problem instance is, because we're going to be talking about the hardness of problems, what their runtimes are, as a function of the input size. Okay? So the size of a problem instance, or the size of a problem input, we're going to label that, we're going to denote it size of I, where I is an instance or input. It's going to be the number of bits needed to write down the instance. Okay? So it's the number of bits needed to write down the input. And that, of course, depends on exactly how you decide to write down the input. Right? You might write it down in a very efficient way, or in some extremely strange way, some very inefficient way. And so our complexity results are supposed to be in terms of this number of bits needed to write down the instance. It shouldn't be some weird, undefined thing that depends on the input representation. It should be a real definition that we can latch onto and prove good theoretical results about. So we're going to talk about in this lecture a little bit later how size I is really defined precisely. Okay, and of course we're going to talk about the relative hardness of problems. So what we're going to do is we're going to take problems, decision problems specifically, well primarily, we're also going to talk about some other non-decision problems where the output is not just true-false. But for the most part, we'll talk about decision problems. We're going to classify decision problems especially into a hierarchy of complexity classes that have various relationships between each other. And so I'm going to define for you this first complexity class, which is a very important complexity class. It's called P. Okay, so we'll define what this means, but first I have to define what an algorithm that solves a decision problem is. So what's an algorithm that solves a decision problem? Well, an algorithm A solves a decision problem pi, provided that A finds the correct answer, yes or no, for every instance of I. So it has to be a single algorithm that will work for all possible inputs. And it has to also solve every possible input, producing the correct answer in finite time for each input. There can't be any input for which it runs in infinite time, or for which we don't know if it terminates. Okay, that would not be an algorithm to solve a decision problem. Termination is part of arguing that an algorithm actually solves the problem. Okay, and now something slightly stronger than saying it terminates is to say that it terminates in a certain amount of time. It terminates in a polynomial amount of time. What do I mean by polytime? Well, an algorithm A is a polytime algorithm for a decision problem pi if the complexity of A, the runtime complexity of A, is order n to the k, where k is a positive integer and n is the size of I. It's the number of bits. Okay, so if we have an algorithm that solves this problem pi for all possible inputs of size n, all possible inputs that I can write down using n bits, if I can solve all those inputs in at most order n to the k time for any positive integer k, then I have something that's polynomial time. Okay? And I want to pick a single k that works for all possible sizes n. So if I can say, look, for every possible input size n, I know that I'm able to solve that problem with this algorithm, and it'll run in at most n to the 100 time for all possible values of n, then you've proven that you have a polynomial time algorithm. So it can be any fixed constant, k, that works for all possible values of n, and you're good. You've shown polynomial time, and we'll get more into that. Okay, so what is the complexity class P? Well, it's the set of all decision problems that have polynomial time algorithms to solve them. Okay, so if there is a polynomial time algorithm to solve a problem, that problem is in P. Now, do we need to know what that polynomial time algorithm is? No. This is not the class of algorithms for which we know, this is not the class of problems for which we know polytime solutions. It's a class of problems for which polytime algorithms exist. Maybe we haven't discovered those algorithms yet, but it doesn't change whether the problem really does belong in P. But if we don't know an algorithm that runs in polytime for that problem, we simply can't prove that the problem is in P. We just don't know if it's in P in that case. Okay? But if we actually derive a polytime algorithm to solve a problem, then by doing so, we've proved that that problem is in the complexity class P. There is an algorithm that solves the problem in polytime. Okay, so let's talk about some sort of problems that we've seen throughout the course and some ones that we haven't that seem on the surface like they're quite similar, but actually have very different complexities. Depending on slight variations to the problem, and some other problems that seem very, very different on their face. One problem can seem much harder than the other, but in fact, they have very similar complexities. So if you look at these knapsack problems, we have this decision knapsack problem. It's a 0-1 knapsack where you either take an item or you don't. You can't cut the item in half. It loses all of its value if you do that. So you have to take a whole item or none of the item. Of course, you have these sorts of items on the right? And then there's the rational knapsack problem, which is also a decision problem because we're going to express it in this way. Sorry, I should have said for the 0-1 knapsack decision problem. This is very similar to the 0-1 knapsack problem we saw earlier, but this is 0-1 knapsack decision. So what do I mean by decision? I mean that we can only return true or false. So how do we express the output to this problem naturally and get true or false as a reasonable output? Well, we can have a list of profits for each item as input, a list of weights, a weight for each item, a capacity, and a target profit T. Okay, this target profit T wasn't in the original 0-1 knapsack problem formulation. The rest of the arguments were, but this input, target profit T, was not there. And so we're going to ask, is there a way to take some of these items, some subset of these items, such that we've respected the weight limit, we haven't taken too much weight, but we've made at least T profit. So the decision version of this problem is, can I solve 0-1 knapsack on this problem instance such that I can get at least T profit? Yes or no? Okay? And then there's rational knapsack, which is defined the same way, except that we're allowed, rational knapsack decision is defined the same way, except we're allowed to sort of slice up our inputs and take a fraction of a particular input item. Okay, so it's sort of like, this is the bulk barn knapsack decision problem. And you would think, maybe these two problems would have, similar hardness, perhaps, especially if you saw that we had a greedy algorithm to solve rational knapsack, right? By the way, if we want to solve rational knapsack decision, you can still use the greedy algorithm to do that, right? All you have to do is run the greedy algorithm, which takes all the same arguments, except it doesn't take the target profit T. The greedy algorithm tells you what the best profit you can achieve is, and then you just test, is that best profit at least as good as T? If so, you return true, else you return false. That's how you solve rational knapsack decision using rational knapsack greedy solution that we saw in class. So you can solve this, and that greedy solution ran in polynomial time in the input side. So this is solvable in polynomial time. This problem up here is actually among one of the hardest types of problems that we actually have encountered. This turns out to be an NP-complete problem. NP-complete, we'll see in a couple lectures, is this enormous class of problems that are all basically equivalently hard for some definition of equivalent. And if you can solve one of them, you can solve all of them. If you can solve one in polynomial time, you can solve all of them in polynomial time. And people have spent 40, 50 years trying to figure out, can I solve any of these problems in polynomial time? And so far, nobody knows a polynomial time solution to any of these, actually hundreds of problems. I think hundreds is conservative. So this, for all intents and purposes, this is about the kind of almost the hardest type of problem we know of. So there's actually a huge complexity gap between these two problems. In terms of known algorithms, there's an exponential time complexity gap between these two problems. Okay, so let's look at, so those are two problems that look very similar, but are incredibly different in complexity. Let's look at, two more problems that sort of fall into that same category. So the problem of finding a cycle, we've treated, in a graph, we've treated that problem in this course, right? So you just kind of run a depth-first search and check for back edges, and you can figure out really easily if there's a cycle in your graph. And you could do that in Poly-time. Now, looking for a Hamiltonian cycle, that turns out to be much harder. So what's a Hamiltonian cycle? It's a cycle that passes through every vertex in the graph exactly once. Okay, so you could, use, any subset of the edges of the graph, but you should pass through every vertex exactly once. You have to visit every vertex once and no more than once. Okay, so doing that turns out to be incredibly difficult. So sort of just to give you some idea, cycles and graphs here. I found a cycle on the graph. This is a Hamiltonian cycle. The edges listed, shown in blue. These ones form a single cycle that touches every node in the graph exactly once, right? Okay. So, you would think these look, not that much harder, but, or not that different, but it turns out the Hamiltonian cycle, the best known algorithm that we have, there's an exponential gap in complexity between these two problems. Okay, so how do we actually start to reason about the relative hardness of problems? How do we say that one problem is not really much harder than another? How do we say this problem is, at most as hard as that other problem? How do we say, for example, that rational knapsack decision is no harder than rational knapsack? Because we had a greedy solution to rational knapsack, and once we have that solution, I can do this reduction from rational knapsack decision to rational knapsack by just sort of running rational knapsack and then just testing if the value it returns is greater than or equal to the target profit that we would like to achieve. So sort of once I know that reduction, I've sort of reduced the problem of solving rational knapsack decision to this other problem of solving rational knapsack. And so when rational knapsack is solved, it's not really any harder for me to solve rational knapsack decision. I sort of want to be able to express that using reductions, that rational knapsack decision is no harder than rational knapsack that I can solve in a greedy way. But the question is, I have to define what it means to be no harder. What does it mean to be harder or about the same difficulty as? For us, in this course and in a lot of computer science, we sort of consider a problem to be very hard if it's exponential time and sort of easy if it's polynomial time. So when we talk about a problem being harder than another problem or about the same difficulty as another problem, if there's only a polynomial time complexity gap between the two problems, meaning if I can solve one problem in polynomial time, then with some, polynomial time overhead beyond that, I can solve another problem pi 2. Then I can sort of say, well, if I can solve pi 1 in polynomial time, I can also solve pi 2 in polynomial time. So they're sort of equivalently difficult. Well, not equivalently, sorry. Pi 2 is, it's only polynomially harder than pi 1, at worst. I've shown with my reduction in that case that if I'm solving pi 1 using pi 2, by reducing to pi 2, then, if I have a polynomial time reduction from pi 1 to pi 2, then pi 1 is only polynomially harder than pi 2. And if I take, a solution to pi 2 that runs in polynomial time and I plug it in as a subroutine and I solve now pi 1 by using this polynomial time solution to pi 2, then with pi 1, I'm sort of going to do polynomial extra time, and then I'll do a polynomial time call for pi 2, and all of that will combine to just become one big polynomial time algorithm. And so I can sort of say, look, if I can solve pi 2 in polynomial time, and my reduction tells me I can solve pi 1 in polynomial time as well, then pi 1's not really any harder than pi 2. They only differ by a polynomial factor. That's fine, who cares? I'm just going to say that pi 1 is not really any harder. And if I want to say that two problems are polynomially equivalent, that they're basically equivalent in terms of running time up to a polynomial factor, then I could just show that I can reduce pi 1 to pi 2 in polynomial time, and I can also reduce pi 2 to pi 1 in polynomial time, then they're actually equivalent up to a polynomial factor. Okay, so this is very much like the reduction we saw before. We've of course seen reductions, I think in all 5 sections of the course since like lecture 3 or something like that. So we've all seen reductions. We've all been working on them. We've solved assignment problems that are reductions. What's the difference between the reductions we've seen so far and this polynomial time Turing reduction? Okay, so for this polynomial time Turing reduction, we're going to have 2 problems, pi1 and pi2, that are not necessarily decision problems. They might return things that are different from true-false. And then we're going to have some hypothetical algorithm B, an oracle, that solves the subproblem pi2. So we're going to reduce problem 1 to problem 2. Problem 2, we're going to assume we have this oracle algorithm B that solves pi2, and we're actually going to assume that B runs in constant time. And the purpose of assuming that B runs in constant time is just to kind of allow us to analyze the complexity of the reduction from pi1 to pi2, where the runtime of B is not really a factor. And then we'll be able to argue that regardless of what the runtime of B is, if it's a polynomial, that's fine. We'll still end up with a polynomial time algorithm to solve pi1 if we have a polynomial time reduction and a polynomial time solution B to the subproblem. Okay, so you have this black box algorithm B that you can call to solve problem pi2, the subproblem, in constant time. And suppose that you write such an algorithm that solves pi1. Okay, so you're going to write an algorithm to solve the bigger problem pi1. You're going to use that oracle to solve pi2 as a subproblem, somehow using that oracle, maybe calling it a bunch of times, feeding in, massaging your input to problem 1 so that you can feed it into B, which will then solve that problem as an instance of problem 2. Maybe you call B a few times, you take all the output of the oracle from all those calls, you combine all that output together somehow, and you produce a correct result that solves problem pi1. Okay? So in that case, A is a Turing reduction from pi1 to pi2. What makes it a Turing reduction is these problems, pi1 and pi2, can be any problem, not just decision problems. And later we'll look at a restricted type of reduction, of polytime reduction, where we only allow decision problems. Okay? But for here, we're going to allow any type of problems, not just decision problems. Okay, we'll write that pi1 reduces to pi2, and of course pi2 here is the subproblem. We have this black box solution to pi2, and I always remember which direction this arrow thing goes because it sort of looks like an arrow, right? And it's saying pi2 is going into pi1 as a subproblem. I've got the subroutine for pi2 that's going into pi1. I'm going to solve pi1 using that subroutine. Okay? And what does it mean for this Turing reduction that solves problem pi1 in terms of problem pi2? What does it mean for that to be polynomial time? Well, it means that the running time of that reduction, just the code, to solve problem pi1 using these calls to B, is polynomial time under the assumption that B has a unit cost, O of 1 time, right? And if there is a polynomial time Turing reduction from pi1 to pi2, we write pi1 less than or equal super t sub p pi2. Okay? What does it mean to be polynomial? Polytime, it means that your polynomial in the time, your polynomial time in the input to problem pi1. You're trying to solve problem pi1, so that's what it means. The reduction should be polynomial in the input to pi1. Okay? And, for example, we could reduce all pairs shortest paths to single source shortest path, right? So I mentioned this in my sections, probably the other sections mentioned something similar. You could reduce all pairs shortest paths to single source shortest paths by making a bunch of calls to a solution to single source shortest path. You could make a bunch of calls to Bellman-Ford, B the oracle would be Bellman-Ford. You make a bunch of calls to Bellman-Ford, you combine the output to get your output matrix of distances. Okay? And you can actually argue that that would be a polytime reduction because you would do at most one call to the oracle for each vertex in the graph, and we'll sort of see more about that later, but you can sort of see that that's polynomial number of calls. The number of calls to the oracle will be polynomial in the input size, and everything else we do in that reduction would be polynomial in the input size. So that would be a polytime reduction from all pairs shortest paths to single source shortest paths. Okay, and that's just there for your notes. And so just at a high level, a reduction typically transforms the larger problem's input so it can be fed to the oracle. And then you call the oracle maybe once, maybe a bunch of times, and then you collect all the output that you got from your calls to the oracle, and you combine all of that to form a solution to the larger problem, and you return that solution. Okay, so let's talk about let's talk about this problem called the traveling salesperson problem. Which is very related to finding Hamiltonian cycles, and will show Turing reductions, polytime Turing reductions between all variants, these three variants of this problem, to show that actually all three of these problems are polynomially equivalent, meaning if you could solve one of them in polytime, then you can solve all of them in polytime. And actually, we don't know, us computer scientists don't know, any polytime solution to any of these problems, and we think they're all about as hard as any problem that we know how to solve. So TSP decision turns out to be an NP-complete problem. It's an extremely hard problem. But these are all, within a polynomial factor of each other. If you could solve one in polytime, you could solve all of them in polytime. And as we'll see, these three different flavors of this problem, only one of them is a decision problem. And so let me sort of run down these definitions for you. So here's TSP optimization is the first problem. So what we take in as input is a graph, a directed graph. Actually, I don't think it matters whether it's directed. It's just a graph and edge weights. And the weights are positive integers. And the goal is to output. So what is your output? It's not true-false. It's a Hamiltonian cycle. So a cycle that visits every vertex in the graph exactly once. And it's not just any Hamiltonian cycle. It's a Hamiltonian cycle that achieves the minimum sum of weights on that cycle. Okay, so it should be the minimum out of all Hamiltonian cycles in the graph. We want the Hamiltonian cycle in the graph that has the minimum sum of weights. Okay, so we're outputting an actual cycle here. So the return type is a path or cycle. The second problem, the return type is a positive integer. Okay, so same problem setting as the first. But in TSP optimal value, what we want to return is actually that optimal sum of edge weights. So not the actual cycle, but just on the optimal cycle, what is that sum of edge weights? So that's the minimum value t, so that there is a Hamiltonian cycle with a sum of weights equal to that t. Okay, so we're going to return a positive integer t, and TSP decision is the decision version of this problem. The question is, does there exist a Hamiltonian cycle with weight at most t? So can we achieve weight t or better with a Hamiltonian cycle? So the return type here is yes, no. And I'm going to show you that these are all actually polynomially equivalent, which has an interesting consequence. So if I have a solution to TSP decision, then I have, that's polytime, then I have polytime solutions to these other flavors. So that tells me if I can get this sort of single bit of information out of TSP decision, and I can sort of solve this problem in polytime. I can make some number of calls to TSP decision, some polynomial number of calls to TSP decision, and I can somehow combine this like single bit response that I'm getting from each of these calls to actually reconstruct not only the optimal value t, but a complete Hamiltonian cycle that achieves that optimal value with only polynomial time overhead. So what this suggests is there isn't actually a huge gap between the complexity of a decision problem and a non-decision problem, if you're, at least for many important problems. And so this sort of suggests that if we want to consider the hardness of problems, it's actually enough for us to restrict our attention primarily to decision problems, because the gap between a decision problem and the non-decision variance of that problem is typically only polynomial, which means that wouldn't warrant considering the decision problem instead of a non-decision variant of the problem, wouldn't really justify in most cases. It wouldn't change the question in most cases of whether this problem would fall into the same or a different complexity class from another problem we'd like to compare to. So usually we can compare just the decision versions of problems to each other to establish hardness results. And so the first reduction I'm going to describe here is incredibly simple. So simple we can just walk through it together without me showing anything else in the slides. So we're going to note that TSP decision can be reduced to TSP optimal value. In other words, if I have a solution to TSP optimal value, then I can solve TSP decision in polytime. Okay, so I'll give you a second to think about how you would do that. Okay, so pause if you'd like to do that. Okay, welcome back. So the way you would do this is we want to solve TSP decision. Okay, so we have as our input G, the graph, edge weights W, and a target T, and we want to ask, can we beat target T? Can we match target t or beat it with a Hamiltonian cycle in the graph? Well, just run TSP optimal value on the graph and the weights. It will tell you what the best you can do is. See if that's less than or equal to t. Done. That will run in polynomial time because all we're doing is calling TSP optimal value once. We assume that takes O of 1 time because it's our oracle. And then we just do O of 1 time to check if the value that we get back from TSP optimal value is less than or equal to t. If it is, we return true. If it's not, we return false. That's it. That establishes the existence of a polynomial time Turing reduction from TSP decision to TSP optimal value. So now I'll ask you, can we reduce TSP decision to TSP optimization? How would you do that? So pause if you'd like to do that. Okay, welcome back. So the way you would do this is you would just sort of say, let me run TSP optimization on the graph. It'll run in O of 1 time. It will return a Hamiltonian cycle that achieves the best possible weight. Sum up all of the edges on that cycle, traverse the cycle and sum up all the edges. Get your t value from that. And then just check, is that t value less than or equal to the actual target that we got as input to TSP decision and return true or false as appropriate. Okay, so we've shown 2 reductions already. Okay. By the way, all this stuff up here is here for your notes. I already said this stuff on the previous slide. So we know we just argued these 2 reductions. We're going to show one more reduction here, and then we're going to show that we're showing 2 more reductions actually. We're going to show TSP optimal value is Turing polynomial time reducible to TSP decision. So in other words, if we have a solution to the decision problem, we can solve the optimal value problem. And I'm going to show that if we have a solution to the decision problem, we can solve the TSP optimization problem where we return the actual cycle. And there's only polynomial overhead. If you have a solution to TSP decision that's O of 1 time, we can solve both of these problems in polynomial time. Time that's polynomial in the input size to TSP optimal value, and time that's polynomial in the input size of TSP optimization, respectively. Okay, so let's see the reduction from TSP optimal value to TSP decision. Okay, so we're trying to get what is the minimum weight such that there is a Hamiltonian cycle with that weight. And we have available to us an oracle that can answer in constant time queries of the form, does there exist a Hamiltonian cycle H with weight at most t? Okay, so suppose we have, some graph here. This is an input to TSP optimal value because that's the input we're provided. We're trying to solve the problem TSP optimal value. Here's the input. We get a graph and we get edge weights. Okay? And now we'd like to use TSP decision to solve this problem, but TSP decision, it takes not only a graph and weights, but also a target. So we have to feed a target into TSP decision. So if I want to figure out what's the best weight that I can achieve on any Hamiltonian cycle in this graph, let's try to call TSP decision, on this graph with these weights with some t-values. Let's say I say the t-value is 100. Okay, what will TSP decision say? Okay, it'll return true, right? There is a Hamiltonian cycle that achieves weight 100 or better, right? So in particular, we can contrive such a cycle here. From here to here, there's an edge weight of 1 plus 5, that's 6, plus 1 to get to this node, that's 7, plus 1 to get to this node is 8, plus 3 is 11, plus 3 is 14, plus 2 is 16. So we can visit all of the nodes exactly once by following those edges with a weight of 16. Okay, so the TSP decision is definitely going to return true. But we don't learn the optimal value by calling TSP decision, right? We just learn that the optimal value is less than or equal to 100. So, how can we take this solution further? Should we call TSP decision again? What should the argument be? How should we call TSP decision to solve this problem? So if you want to take a moment to try to solve that, you should pause now. Okay, so here's the idea. We sort of want to make repeated TSP decision calls, right? So we could call it with 100, and then we could call it with 99, and then we could call it with 98, then we could call it with 97, and we could do this until the first time TSP decision returns false, right? The first time it returns false, we know right before it returned false on the previous solution we had exactly the optimal value, right? But that would be very inefficient. We might have to make a huge number of calls to TSP decision. In particular, what's the largest value that we sort of might have to start. So first of all, we started from 100. Why did I start at 100? I just guessed a number that was higher than the real optimal value. But really, I need some place to start if I'm going to start at the largest possible value I could get, and then I'm going to decrease all the way down to 0 and find the first point where I returned false. By the way, the opposite strategy also works fine. If I start at 0 and increase until the first time I see true, maybe that's even less confusing. So let's say I did that. I just start at 0 and I increase until the first time I hit true. So I call TSP decision GW0, call TSP decision GW1, GW2, GW3 until the first time when it returns true, and I know that's the optimal value I can achieve, whatever number I invoked in place of whatever t value I proposed here. Okay, so how many of these TSP decision calls am I making in that case? And how far do I have to go until I sort of know I'm done? When can I, if I don't see true for a very large number of calls, sort of maybe there is no Hamiltonian cycle in this graph. Maybe the graph is disconnected and there isn't a Hamiltonian cycle. It's got a huge cut down the middle of the graph, and there is no Hamiltonian cycle. How do I know that I should stop? I shouldn't invoke TSP decision forever on ever increasing edge weights. There should be some upper bound. Well, the largest Hamiltonian cycle weight I could get is certainly smaller than just the sum of all the edge weights in the graph, right? If the cycle included every single edge in the graph, then that would be just the sum of all weights. Okay, now it can't be any bigger than that. The weight of the cycle can't be bigger than the sum of all the edge weights in the graph. So I can stop as soon as I go through the sum of all the edge weights in the graph. Well, it turns out that that's incredibly inefficient. That will end up being exponential time in the size of the input, right? Because we're going up to the sum of the values of the weights, not the number of bits needed to write down the weights, but the values of the weights. And the value of a weight is exponential in the number of bits needed to write it down. So if we're going up to the sum of all the values of the weights, that can end up being exponential in the number of bits needed to write down all those weights. So we'll end up with an exponential time solution. That's not going to give us a poly-time Turing reduction. So we need to do better than just making these calls one by one. So what can we do? Okay, so again, if you'd like to take a crack at that, you can pause. Okay, welcome back. So the solution here is going to be to use binary search, right? And so as long as we can define a range from low to high where we sort of know what the extents, like the real true optimal value that we're searching for is between low and high, why not binary search it? Because we have this nice monotonicity property on that range, right? If we're querying a number t that's greater than the optimal, greater or equal to the optimal, TSP decision solver will return true for every number greater than or equal to t. It'll return false for every number less than t. So we have this monotonic switch. So this is effectively a sorted range that we're searching, and we're searching for the first one in a sorted range. So we can actually binary search that. So we'll set our high endpoint to be the largest possible cycle, which just, we'll overestimate it with the sum of all the edges. The lowest possible weight is if it's just, a graph with one node and there are no edges and the edge weight's 0. Right? We'll assume that there are no negative weight edges, just for simplicity's sake in this. I think the problem gets harder if you have negative weight edges, so let's assume there are no negative weight edges. In the real world, you care about this problem for things like a delivery truck visiting every stop on its route exactly once and then returning home, and the minimum sum of, the minimum weight of that cycle is the minimum distance traveled to visit all the stops and return back to the, and then possibly return back to the depot at the end. So in the real world, the costs of those edges are all positive, right? So 0 is going to be the smallest possible weight for any cycle. And then we're going to, first of all, check, is there a solution? Okay, so we're going to run TSP decision solver. It'll tell us for the high endpoint if there's a solution or not, right? If there's no solution, when we're running for the high endpoint, there's no Hamiltonian cycle with weights all the way up to the sum of weights in the graph, all the weights in the graph, then there is no Hamiltonian cycle. We just return infinity. Okay, that's going to be the optimal value, is just infinity. And then otherwise, we're going to binary search here. So while high is greater than low, we'll take the midpoint of that range. We'll test the midpoint of that range. So we're going to test if we can solve finding the a Hamiltonian cycle with total weight mid or less. If we can find with total weight mid or less, then we'll set high to mid. Okay, we can certainly find it with weight. We know weight mid is good, so we'll include it in the range. We'll throw away everything above mid. Okay, because we don't need to search any of those. We know we can do it with mid, and sort of the opposite for low here. If we can't do it with mid, we'll throw away everything below mid, including mid, because we can't do it with mid. So what we're maintaining here, did I write down? Oh, no, I didn't. Okay, so the property we're maintaining as we do this binary search is that the optimal value we're searching for is always trapped precisely between low and high inclusive. Okay, so when we terminate, we'll terminate when high is equal to low. At that point, we will have trapped the true value between low and high inclusive, so it'll be exactly equal to high, and we'll return the correct answer. Okay? So we'll argue that this is a correct solution. Is this a poly-time reduction? Well, if we assume that TSP decision solver runs in O of 1 time, okay, so these are all O of 1, the question remains, does this have runtime that's polynomial in the input size? And so you have these two questions. What's the input size, and what's the runtime? Okay, so let's start with what's the input size. So remember, the input consists of a graph and some weights, and the graph, of course, consists of vertices and edges. So really the size of the input is sort of the size of the vertices plus the size of the edges plus the size of the weights. Okay, now suppose the graph is represented as an array of adjacency lists. This is one list for each vertex, and each list contains edges to the neighboring vertices, where an edge is represented by not only the name of the target vertex, right? So you have an adjacency list. Each element of the adjacency list, we have a little struct with it's like a pair. Each element of the adjacency list is a pair consisting of the name of the target vertex. So I'm going from, the list for node U contains pairs where each pair is the target of that edge, node V, and the weight of that edge, some W from U to V. Okay? Then the size of I is going to be something like this. It's going to be, theta the size of V, assuming we can sort of represent one vertex in, a constant amount of space. So, we're going to sort of initialize an array of pointers to the head of an adjacency list. Okay, so this is an array with one slot per vertex, and we're assuming that this array is going to be like one slot per vertex with each slot representing a pointer to the head of that vertex's adjacency list. And we're assuming here that we can store a pointer in O of 1 bits. And then we have a sum of some expression for each edge in the graph. Okay, for each edge, we're going to have to store something. That's going to be the weight of the edge. Okay, so the weight of the edge UV, that's the actual value. How many bits do we need to write down the value of WUV? We only need log UV bits to write that down. And then we have log size of V, log cardinality of V. This is really log n, right? Number of nodes. So this is if we want to write down any number from 1 to n, we need order log n bits to write that down. So if you want to write down one of the names, if the vertices are named 1 to n, and we want to write down one of those names, we need log n or log cardinality of v bits to write that down. Okay, so this is saying, look, here's the pointers to the heads of my adjacency list, and then here's the nodes of the adjacency lists. For each edge, there's a node in some threads, some vertex's adjacency list, and that node in the adjacency list, that struct in the adjacency list is a pair containing the weight of the edge and the name of the target vertex. Okay, so this is the size in number of bits. So what would it mean to have a runtime t that's polynomial in this size? What does it mean to be a polynomial in this crazy expression? Well, we say t is polynomial in size of I. We denote that t is in poly of size I. If and only if there exists a constant c such that t is in size of I to the c. Okay, so you take this whole gnarly expression and we want to have O of this to the c. Well, what's this to the c? It's quite a complicated expression, right? And O of this to the c means you can have terms that are like some constant multiple of size of I to the c, plus terms that are some constant multiple of size of I to the c minus 1, to the c minus 2, to the c minus 3, and so on, all the way down to size of I, and then plus some constant at the end, right? So this could be a really complicated expression. And really it describes anything that's less than or equal to some, size of I to the c for some c, right? So it could be tons of very complicated expressions here. You just have to show that t is at most some constant times size of I to the c for some c. Okay, and if you can show that, then you've shown that t is polynomial in the size of I. Now this c that you pick, this has to hold for all possible inputs, okay, and all possible sizes of inputs, okay. So this has to be one constant c. Okay, so fix a single. This is like c is going to be like 100. You're going to show for my algorithm, it's at most the size of the input to the 100. So it's a fixed 100 that works for all possible inputs of all possible sizes. If you can show that, then you've shown that your solution runs in runtime that's polynomial in the size of the input. Okay, but wait, the size of I depends pretty heavily on how we represent the input, right? So the vertices and the edges and the weights could be represented in tons of different ways. We might have adjacency lists, adjacency matrices. Is it the unit cost model where we assume that our weights can be written down in a single word of memory so that accessing them should be O of 1 time and they're stored in O of 1 space? Or should we be not using the unit cost model and these weights should take log of WUV space and take log of WUV time to access? The choice of representation of the input might end up affecting our complexity result. It might even change the outcome. You would imagine it might change the outcome of whether something is polynomial, whether your algorithm is actually polynomial in the size of the input could depend on how you represent that input. Okay, now this is true. The choice of representation could actually change whether your algorithm is polytime in the size of the input, but actually only for very inefficient representations. So by an inefficient representation, I mean an input representation that's exponentially larger than the optimal representation. And I'm not going to define that super carefully. There are some bonus slides in the end that try to explain this in more detail. I'm not going to cover them, but you can look at them if you're curious. For example, though, if we stored these weights, we didn't even store them in binary, so we weren't storing them in log WUV space, because log WUV space, log base 2, of WUV is how much space I need to write down this value in binary. If I want to write down this value in unary, it takes me WUV bits, right? If I want to write down 100 in unary, I have to write down 100 actual ones, right? If I want to write down a million, I need a million bits. So if we store weights in unary, that's exponentially more inefficient than storing weights in binary. That can end up changing your runtime complexities and making algorithms that are actually exponential time look like they're polynomial time, because they're polynomial in this gigantic exponential input. Okay? We're going to rule out such inefficient representations. So we're going to talk about reasonable representations in this course as being sort of polynomially equivalent or close to optimal within like a polynomial factor of optimal. Okay, and those are going to be the sort of reasonable representations that we're going to use for proving polynomial time. And here's an exercise for you. This isn't a pause and do it. This is a do on your own time. So my claim here is that polynomial differences in size of the input don't matter from the perspective of showing that your algorithm is polytime. So for example, here's an exercise. So show if you have an algorithm that runs in polytime, but it's polynomial in the size of the input to the 40. Then show that t is also polynomial in just the size of the input, right? So raising size of the input to the 40 doesn't actually change anything meaningful, right? So in fact, I think you can show this if and only if. So I encourage you to try doing that. You can prove this both directions, and you can argue to yourself that polynomial differences in input size don't matter from the perspective of the question, is my algorithm a polytime algorithm or not? So what I'm going to do is I'm going to give you this input size cheat sheet, okay? So these are sort of input sizes that you can use that are perfectly fine when you want to do your polytime analysis. So if you have like an integer x, that's your input, then like 1 is a fine choice of size. Log x is also a fine choice of size. When there are alternatives for all of these representations, you can pick any expression that makes your analysis easy, okay? Now, in many places in the course, we've said, well, don't pick 1, because then your complexity will change, right? 1 is exponentially different. Well, it's not even exponentially different. It's completely unrelated. It's constant, and log x is not constant, so it definitely changes your runtime. But here you can pick any of these choices that actually work for you, because if you pick an input size that's too small, you pick your as an input size 1, you may have trouble showing that your algorithm is a polynomial function of the input size. Your algorithm runtime is bounded by a polynomial in the input size, because what's a polynomial in the input size? It's 1 to the c, for any c is just 1. So you're only an algorithm that's constant time could you possibly show is polytime in the input size if you let your input size be 1. So if your runtime is not constant, you better pick this larger value. Right? So pick log x in that case. So you can pick whatever expression makes your analysis easy. So here are fair expressions to use for a graph. You can use just the size of v. This is like n. You can use the size of edges, number of edges. That's just e. You could use like the number of vertices squared. You could use cardinality of v plus cardinality of e. You can use the sum of all edge weights over all the edges in v. In e, sorry, of like log of log we. So the number of bits needed to write down all the edges for each edge. All the weights for each edge, or you can do the size, the number of bits needed to write down all of the weights for each pair of vertices. That's fine. You can do any sum of these terms. In fact, you can do any pseudo-polynomial combination of these terms. What do I mean by pseudo-polynomial? I mean that there's no exponentiation of any terms except for constants. Okay, you can raise to the constant. You can't go 2 to the v. You can go v to the 2. That's fine, because 2 to the v would be exponentiating something that's not a constant. So you can't do any exponentiation unless you're exponentiating what you're putting in the exponent is a constant. Okay. So any pseudo-polynomial combination of these terms is fine. For example, the following is fine for a graph. You could do the edges to the 100 plus number of vertices squared, all of that times the sum of the number of bits needed to write down all the edge weights for edges. Okay, so if this happened to look very similar to your runtime for your algorithm, you could let your size be that, and you could easily prove that your algorithm is polynomial in this. Okay. And now, for an array, you could just sort of say, look, I could let the number of elements of the array, if I'm sort of assuming that each element takes a constant space to store, or I could do like the sum of, log ai, so how many bits I need to write down ai over all the i's, right? And for a matrix is sort of similar. Okay, so those are the perfectly fine choices of size I. What are invalid choices of size I you cannot pick? Okay, there are other possible invalid sizes. These are just some examples to give you a taste for that. Okay, so if you have an input that's just an x, okay, you can't pick x as the input size because you can write down x in log x bits. X would be exponentially larger than that optimal representation. So you can't pick x. Okay, you can't take 2 to the v for a graph because that's exponentiating something that's not constant. Clearly, this is a very inefficient representation. Can't do v to the e. Can't do the sum of weights. You have to do the sum of log weights, right? So log weights, number of bits to write down the weights. The sum of weights could be exponentially larger than the sum of log weights, right? So that's too inefficient a representation. It's an exponential gap, not a polynomial gap. Similarly, for an array, you couldn't do like 2 to the n. You can't sum up the actual values of the array elements. These have exponential gaps between these terms and these terms. So these are not okay. Do not use these input sizes for or anything like this or any exponentiation of non-constant terms in your input size selection. Okay, so how do we do the input size analysis? Well, for TSP optimal value, we're going to sort of pick a size from our cheat sheet table that's convenient for our analysis. So let's see, we're going to pick something that's close in form to our runtime. So what's our runtime? Let's compute that. So let's assume O of 1 times for operations on weights. And later I'll show that this O of 1 time unit cost assumption actually doesn't make a difference really in terms of whether this is a polytime reduction or not. If we assumed that accessing weights took log size of the weight time, we made like a not the unit cost model assumption. If we had a non-unit cost model, it wouldn't make a difference to the question of whether this is polytime. Okay, so let's ask, how long do each of these steps take? Well, here we're summing up all the weights. Under the unit cost model, adding each weight to a sum just takes O of 1 time. So this is cardinality of E. This is order M. This just takes order 1. This TSP decision solver call, it's a call to the oracle. That takes O of 1 time. And then the number of iterations here, well, it's a binary search, right? So it's log of the size of the range that we're binary searching. What's the size of that range? It's high minus low, right? So the size of the range is high minus low, and high minus low is just this sum minus 0, right? So it's log of this sum. That's how many iterations we're going to have. And in each of those iterations, what are we doing? We're doing constant time at this line, constant time at this line, constant time at these 2 lines, okay? So it's all constant time. And constant time to return. So the total runtime is going to be order cardinality of E, that's M, plus these constant things, plus log sum of weights. Okay, it's the log of the sum of weights. Okay, and we can sort of simplify the e term is going to be dominated here because it's where for each e, each little e in big E, we're summing the weights. Then we're taking the log of that. My claim is that'll dominate the e term. It actually doesn't matter if I remove this e term. If you can't see that immediately, then you can try for yourself as an exercise carrying this e term through the rest of this argument, and it's actually quite easy to see how it disappears. Okay, so we're going to pick the most similar looking input size expression for G out of our cheat sheet table. That was the sum of E and E of log W of E. Okay, so if I go back up to the previous table, I mean, you can click back yourself if you like, you can see that that is an expression. It looks fairly similar to our log. Now, it's a little different from our log expression in our runtime. So how are T of I and size of I related? Well, here's our T of I. We have log sum of weights versus our size of I, sum of log weights. Okay, so it's a little different. Our logs are in different places. So how are these related? Well, the log of the sum of weights, if these are positive weights, if there are no zeros, if these are positive weights, so let's assume that, because in the real world there are no zero costs on these paths. So the log of the sum of weights is going to be at most, it's going to be less than or equal to the log of the product of weights, right? The log of the product of weights, a product of things that are 1 or greater is going to be larger, right? Taking the product is larger than the sum, if they're all positive integers. Okay, and of course the log of the product, right? The log of a product is the sum of logs, right? So that's the sum of logs, and that's actually exactly size I, right? Size I is order this, so I sort of missed an order sign. Sorry, this is supposed to be big O of this. Okay, so the size is big O of the sum of log weights. Okay, so this is order this is going to be equal to size I. Size I is going to be order this, right? These are equal. So in order to say that T of I is polynomial in size I, I'm saying T of I is less than or equal to size I. It's less than or equal to, in fact, 1 times size I. So to argue T of I is in sorry, this should say size of I, not Li. That's a mistake. So to say T of I is poly of size of I just have to say T of I is in fact less than or equal, that's another mistake, less than or equal to 1 times size of I to the 1. Okay, that's clearly a polynomial in size of I, so we're done. Okay, so this is polytime in the size of the input. Now, as an exercise, you might try showing that a variant of this reduction that we saw earlier, where we use linear search instead of binary search, is not polynomial in the size of I. Okay, so this is something you should do offline. I greatly encourage this. Try to show that this is not polynomial in the size of I. Okay, so this is a polytime reduction, but is it a correct reduction from TSP optimal value to TSP decision? It's polytime. Is it correct? Okay, so let's argue that to ourselves quickly. So what we need to prove at a high level is if TSP optimal value solver, this reduction code, if it returns x, then x is the weight W of the shortest Hamiltonian cycle in G. We'll call that Hamiltonian cycle, that shortest one, HC. So what it returns should really be the weight of the shortest Hamiltonian cycle. Here's the proof sketch. If we return here, we return infinity. We're doing that because there's no HC, there's no Hamiltonian cycle. So that's correct to return that. And if there's no Hamiltonian cycle, TSP decision solver will return false. So we will return infinity. So we return infinity if and only if there's no HC, no Hamiltonian cycle. So that's correct. Well, what if we return down here? Case 2. Well, then here's our loop invariant. So W, the true value, the true optimal value, is trapped between low and high. So at termination, when high is equal to low, we're going to return exactly high, which is exactly W, because W is trapped between high and low. Okay, so that's the sketch. I'm not going to prove that in detail. Now, in more complex reductions than this, we sometimes need to transform the input before calling the oracle. Here it's very straightforward. The problems are very similar. We can just call the oracle on basically the same input, GW. If you need to transform the input in a super sophisticated way before calling the oracle, you might need a more complex proof. It would sort of be along the lines of, if there's an optimal solution in the input to like the overall problem, then our transformation will preserve that solution so the oracle can and will find it. So if there's an optimal solution in the input, the oracle will find that optimal solution. And our transformation doesn't in the process of us transforming the input, it doesn't accidentally include any new solutions that are not present in the original input, because that would be bad. The input would find such a solution and say, the oracle could find such a solution and say, hey, there's this optimal input that doesn't exist in the input. That would be bad. So we can't have our transformation accidentally introduce any new solutions that aren't present in the original input. So what this means is if we find a solution in the transformed input, there should be a corresponding optimal solution in the original input. Okay, and we'll say more about this and be more precise about this later. Okay, so this is a polytime correct reduction. So we have shown TSP optimal value is polytime reducible to TSP decision. So if we have an O of 1 time solution to TSP decision, then we have a polytime implementation of TSP optimal value solver, which is it's a polytime solution to TSP optimal value. Okay, now in fact, this TSP optimal value solver remains polytime, even if the implementation of the oracle runs in polytime, not O of 1. Even if this is polytime solution to TSP decision solver, the whole thing is still polytime in the input size to the original problem. Why? Here's the key idea. So consider two polynomials. You have a polynomial for the reduction. It's how many steps are done in the reduction, under the assumption that TSP decision solver is O of 1. And PO is it's a polynomial representing the time the oracle takes. Okay? And this is on an input of size s. And now the worst possible runtime, if we change TSP decision solver, so it's not O of 1, now it's a polynomial, PO of s, then our input would be the worst kind of if, everywhere we had an O of 1 step for TSP decision solver, we replace it with an O of some polynomial in the input, TSP decision solver. Okay, if we do that, the way that we blow up our runtime of our reduction the most is sort of by imagining that every single step in the optimal value solver is a TSP decision solver. Then that would blow up the runtime even more, right? If we replace this with a polynomial, the runtime blows up. If we replace this with a polynomial, the runtime blows up. If we replace this low equals 0 with some polynomial time work, the runtime blows up even more. What if we replace every single step in TSP optimal value solver with polynomial time? So it's getting, even more expensive as I replace every single call. That's the most expensive that this reduction could be if every single step in the reduction is a polytime call to the oracle. But in that case, the worst possible runtime of that reduction would be just every single step is a call to the oracle. Well, that's for each step in the reduction. For every one of those polynomially many steps, we do polynomially many steps in this oracle. It's the multiplication of two polynomials. And if you're curious to see the details of this, you can pause and take a look at it, but I'll just state the claim, and you can see an example. Multiplying polynomials of 2 degrees, d1 and d2, results in another polynomial of degree d1, d2. So it's just multiplying two polynomials results in a polynomial. So what this says is, if I swap in TSP decision solver for another polynomial, for something that takes polynomial time, then however much time this whole thing takes is less than the time a similar procedure would take where I replaced every step with a polytime TSP decision solver call. And that would have runtime that's a multiplication of polynomials. That is a polynomial, so it would still be polytime. Okay? Now we have one more reduction from TSP optimization to TSP decision. But I'm going to leave that for next time. So hope you guys all followed this. Hope you enjoyed the new format. If you have any questions, post on Piazza, and I'll try to answer there. And of course, I think the other professors will also try to answer. If you have any comments about the format or the recording or anything at all, let me know. And thanks for your attention, and I'll see you guys next time.